So we might ask ourselves, what is the original or the primordial atmospheres of the planets? This would be the atmospheres that the planets originally had. You might just assume that the planets that the atmospheres they have now are the ones that they had during the formation, but it's not actually true. At the very beginning, the atmospheres of the planets would have been hydrogen and helium because these are the most abundant elements in our universe. So the question is, how have they changed from them? What caused the changes? Why don't they retain atmospheres of hydrogen and helium? There are different ways that a planet can sort of gain its atmosphere. The three basic processes are outgassing, evaporation or sublimation, and bombardment. Outgassing is when the interior gases that were brought to the planet through the bombardment of comets and asteroids, or created via chemical reactions within a planet, are released during volcanic activity. Basically, what we need to know for outgassing is that volcanoes are responsible for releasing gases that then become part of the planet's atmosphere. This is a very important process on Earth, Venus, and Mars, at least Mars at some point. The gases that we would see through outgassing would be water vapor, carbon dioxide, nitrogen, hydrogen sulfide, and sulfur dioxide. Evaporation and sublimation. Well, evaporation is basically when gases can be, gases might be on the surface, in the atmosphere, but then they might condense onto the surface, and then they also may evaporate back into the atmosphere. So basically what we're talking about with evaporation and sublimation is sort of an exchange between the surface of the planet and the atmosphere, where the gases are sort of going back and forth. Bombardment is when bodies where you don't have outgassing and evaporation aren't important, but when the object is being hit by little micrometeorites, pieces of the solar wind, solar photons, which basically knock atoms or molecules free from the surface rock, and they become part of the atmosphere. This would only create a very thin atmosphere, and this is probably responsible for the very small amount of atmospheric gases that we see on the Moon and Mercury. What's also important is to understand how atmospheric gases are lost. What we're going to really want to understand is thermal escape, because this helps us understand why our terrestrial planets did not retain their original atmospheric gases of hydrogen and helium. There's also solar wind stripping, which played a role for Mars. It can also happen through impacts, condensation, and chemical reactions. So as I said, thermal escape is the very important process that explains why the terrestrial planets did not retain their original primordial atmospheres. Basically, the thermal escape is sort of a balance between the motion of the gas molecules in the atmosphere and the planet's gravity. See, every planet has a certain strength of gravity, and objects can escape from this gravity if they move fast enough. So the escape velocity from a planet is basically sort of a characteristic that helps you describe the relative strength of that planet's gravitational field. The higher the escape velocity, the stronger the gravitational field. And so if gas molecules are moving fast enough to escape from the planet's gravitational pull, then they can be lost. So that's one thing. And then what we have to think about is, well, what determines how fast the gas molecules are moving? Well, the two things that determine it are the temperature of the gas and the mass of the gas molecules. The expression that describes that dependence is right here, where we see the higher the temperature, the higher the velocity. The higher the mass, the lower the velocity. So think about what this means. At the location of where the terrestrial planets are, the temperatures are relatively high compared to other regions of the solar system. This means that all the molecules are moving relatively fast. What will determine or separate out how fast they are moving is the mass of the gas molecules. The heavier they are, the slower they're going to be moving. Well, hydrogen and helium are very light molecules, therefore they will be moving very fast compared to molecules that are heavier, like nitrogen or carbon dioxide. So that helps to explain why the terrestrial planets would have lost their atmospheres of hydrogen and helium very quickly, because those gas molecules would move very fast and they could escape from the planet's gravitational pull very easily. What happened is gradually through outgassing, the planets would build up atmospheres of heavier molecules which would move slow enough to be maintained by the planet's gravitational pull. The Moon and Mercury have very thin atmospheres, which we think is outgassing would have been over long ago. Think about why that's true. There's no volcanic activity anymore. We think that the primary source of their atmosphere is through constant bombardment, and we are actually trying to study these atmospheres in more detail. Mars is a planet that's very interesting to us because there seems to be, in the past, water was flowing on the surface, which means it would have been warmer and it should have had a thicker atmosphere. Basically now, even though it has a high percentage of carbon dioxide, it's not a lot of carbon dioxide. We think that it would have had maybe, its atmosphere would have been 400 times thicker in the past for it to have liquid water on the surface. The existence of the liquid water is sort of substantiated by the fact that there is frozen water in the snow caps that we see on Mars. So where did this carbon dioxide go? Well, as I said, some of it is in the polar caps, and some of it is chemically bound to surface rocks. Some of it might have been blasted away by the impact, and others might have been stripped by solar wind particles. And why would this be important? Well, remember when I said that we're interested in a planet's magnetic field, and that the magnetic field of a planet would be due to some interior warmth which would allow for the core to be in a liquid form. But Mars has cooled since then, and its interior is hardened. So what we're thinking is that early in its history, Mars was much warmer in its interior and had a nice robust magnetic field that would protect it from the solar wind particles that came from the sun. And so this acts as a buffer. As the planet cooled and the magnetic field sort of diminished, the solar wind particles could penetrate the atmosphere of Mars and start to strip away the atmospheric particles. And so as time goes on, the atmosphere becomes thinner and thinner. And because there's no geological activity going on anymore, Mars doesn't have the ability to regenerate that lost atmosphere. So essentially what we see is that the small size of Mars and the fact that its interior has cooled has led to a series of processes that has caused it to lose its atmosphere and grow much colder than it would have been in the past. So to summarize here the things that we know, the terrestrial planets lost their original atmospheres due to thermal escape. The atmospheres of Venus and Mars are similar in composition, but not similar in their thickness. Mars lost its atmosphere when it cooled, and the magnetic field no longer protected it from solar stripping. The thinner atmosphere of Mars makes it much cooler, and water cannot be liquid on the surface anymore. Earth's atmosphere has some atmospheric gases that we don't see on the other terrestrial planets, at least as plentiful. The oxygen comes from actually living things, comes from plant life. The nitrogen also comes from sort of biological processes and outgassing. But why does the Earth have much less carbon dioxide than Venus? Venus is sort of the nightmare of what we could see as the greenhouse effect gone crazy, because Venus has so much carbon dioxide and such a thick atmosphere that it's led to these incredibly horrible hot conditions on its surface. Well, we need to understand the carbon dioxide cycle that we have on Earth. Carbon dioxide is released through volcanic activity, and then it's into our atmosphere. The atmospheric carbon dioxide can be dissolved in rainwater, come to the surface of the Earth, and then go into our oceans. Where here, the carbon dioxide can combine with other elements to create carbonate rocks, which then can also sort of complete the process by becoming part of volcanic activity. So this cycle sort of helps to actually acts as an equilibrium point to keep the right amount of carbon dioxide on Earth. The key here is the volcanic activity and the presence of liquid water. You should read about how the Earth can maintain its stable climate, how if the carbon dioxide gets too thick and it gets too warm, this actually leads to a long process that will help to cool down the Earth. And likewise, if we don't have enough, if it's cooler, the carbon dioxide, the processes can go through a process to help warm it up. Venus is an extreme case of the greenhouse effect. And one of the major reasons we think that Venus isn't more like Earth is because of the lack of liquid water. Once the temperature became so high and the water became water vapor in the atmosphere, which then was broken down by the heat and the solar wind particles, and then once they were lost, the hydrogen and the oxygen was lost, then you couldn't have any more liquid water on the surface. So we really think that liquid water is the key for the difference between the situation on Venus and the situation on Earth. So basically, if we would just be a little bit closer to the sun, it could be possible that the Earth's future would have turned out to be just like Venus's. The carbon dioxide cycle isn't useful on Mars because of the fact that there's no water on it anymore, and because it's not volcanically active, we can't keep the cycle moving. And that's because it was smaller and cooled more quickly. So you might ask, if we have this carbon dioxide cycle and there's sort of an equilibrium thing that happens to keep the temperature at not get too cold or not to get too hot, why do we care about carbon dioxide? And that is because what we are doing through our industrial processes are actually adding to the existing carbon dioxide in our atmosphere. So we're upsetting the balance by adding more carbon dioxide that wasn't there before. And what we've seen is that the global temperatures have actually risen in the past centuries, basically since the Industrial Revolution. And basically, while some people like to think that the global warming is not established, it really is quite firmly established as a scientific fact that this activity is being linked to the warming in the planet. And it has to do with the fact that we've not seen any sort of warming like this in the past, and that we do know that we are adding to the amount of carbon dioxide in our whole cycle, and that's something that we can't really, the planet can't alleviate on its own. And somehow we have to figure out what we're going to do and how we're going to change things to stop this rise in temperatures. And what we see is, this is what we're looking at, is this crazy rise in the past 100 years. And you can see that there's really nothing unprecedented to that in any other time. And this is where we'll stop for now.